Broadly speaking, there is a large number of smart machines, gadgets, and even some smart fully automated systems out there in the world. That includes all of the smart stuff owned by big companies like this smart rover owned and built by NASA, and those robot arms owned by Tesla, and these smart self-driving trucks owned by US military. Only a few in the world makes and keeps them. Now, that number of smart devices reduces drastically when it comes to an average person. It means that not every single person in the world can afford such a smart device. Like these smart watches, refrigerators, air conditioning, and even some smart fully automated homes. But the number reduces to only a few when it comes to the smart stuff that you can build by yourself. Due to the advancement in technology and the fact that the technology is common everywhere, you can build such a smart device purely with your creative mind and these craftsman hands. This is the IoT-based smart plant monitoring system, or irrigation system to be precise. What it does is it actually monitors the plant conditions. It automatically turns on the pump whenever the plant needs water. At first sight, it seems so beautiful, and the engineering behind it is even more amazing. Let me show you how it works. This prototype is for two different crops or plants. We can use a different plant here and a different plant here. Those two valves are able to independently control water flow in both of the spaces. There are two sensors on board which are capable of sensing three parameters: moisture content of the soil, temperature, and humidity in the air around it. Here's the electronics box in which there is a microcontroller and a relay for the pump. All of these wires connect those sensors and displays with the microcontroller. Let me bring in some water. Here's the pump, dip it in, and give it some power. We can see this data on our mobile phone and also on the laptop screen through this interesting dashboard. It is also capable of making live graphs and charts of all of the data it is collecting. We can set a trigger level, which essentially is the percentage of soil moisture on which we want our pump to be turned on. For example, if I want my pump to be on at 25% moisture, I will set this value over here on my phone. And now, when the moisture of the soil here reaches 25%, the system will automatically turn on the pump. Right now it's 33-34% and the pump is off. Soil moisture sensor is dipped in the soil. Here it reaches 22 and the pump is now on. This is so satisfying. I love one of the characteristics of humans very much. They can turn any idea from the rough sheet of paper in reality. In this 4-part video series, I'll tell you the story of how I did it, how I turned this dead raw material to a working model. In this first part, I'll be working with the circuit and electronics of this awesome prototype. I will show you the individual components and how they are connected together. So without further ado, let's get started. The very first thing we need to build any smart IoT system is, of course, a good knowledge of the components we'll use, the circuit diagram which represents how they are connected together, and the piece of software you're going to be using. So the software I am using is called FritzSync. So here is the software called FritzSync. and it is right now, it is loading and doing all of its stuff. So here we go. The software will welcome us with this window. So right now this is really simple. We don't have to worry about all of this stuff. Here in the top right hand corner, we have all of the core parts. So these are all of the simple electronic parts. This is the inspector window, where you can see all of the properties, placements, and all of the this stuff. You don't need any of these right now. So what we'll do is we will go to File here, at this option, File, New, and it will open up this window here. So this is our breadboard. This is our working area. Over here, this is this section is the core parts, as you can see. So for this project, for this IoT based smart irrigation system, we need to construct a circuit diagram on the basis of which we can build our own physical model. So the very first component we need to import here is the ESP32. So this is the ESP32. Here it is. Let me rotate it. Here's this ESP32. This is the microcontroller where we can upload our program, this set of instructions, what this project has to do. So the second component is the relay, let's say. Relay is the electronic switch, which will control our pump later on. Here the third component is, let's say, the OLED display. Here we're importing our OLED display here. Well, this ESP32 will read all of the data from the sensors, and that will be displayed on this OLED display later on. And the fourth component is the DHT22. Here it is. So this is the DHT22, and the last component is the soil moisture sensor. This is the soil moisture sensor. So those are pretty much all of the components, and well, each individual component has its own job to do. So this is the ESP32, which is the microcontroller we are using in this project, which is the Wi-Fi module. Let me open up some of the specifications of this awesome component. This is the real model of ESP32, how it will look like in the real time. Well, now, those are some of the specifications of ESP32. It has the total of 34 programmable GPIO pins where we can read and write our data, and some motor PWM pins, up to 14 channel of LED PWM. So you can read all of this, all of these specifications of this awesome piece of equipment. And this is Wi-Fi enabled, Wi-Fi baseband. The key features of ESP32 is it has some GPIO pins where we can read and write our data. We'll read the data from a sensor, and we can write our data on a pin. So we can use a pin, we can use any ESP32 pin for the purpose of reading and writing our data. So, for example, we connect our sensor. This is DHT22, which is a temperature and humidity sensor. What we can do is we can connect this data pin here with a GPIO pin on this ESP32, and we can read this data, like what is the temperature on what is the temperature around it. This sensor can sense the temperature and humidity around it, and it will send this data through this data pin, and this data pin will be connected to any of the GPIO pin here, and the OLED display will tell us what is the actual humidity is. This is the small, you can say the representation that how simple the basic electronic behind it actually is. We'll go through all of this, all of these components all together, and we'll discuss all of the key features of all of the components. The ESP32 has a total of 30 pins. There are 19 GPIO pins in my ESP32, which I'm using in my real model. It has the total of 30 pins. 19 of them are GPIO pins, where you can read and write all the data, connect all of the sensors, and get the necessary data out of the microcontroller. So these are the two buttons where you can reboot. Well, while programming this component, we have to press this boot button so that it can intake all of the program. So it is necessary to press that boot button while programming. So this button will use for this purpose. This is the reset button, where you can reset your program and reset your microcontroller. This is the 3-volt pin, where you can get the 3 volts from this microcontroller and connect and power all of these sensors. So there will be enough current here in this ESP32 that it can power all of these components, like soil moisture sensor, OLED display, DHT22, through this 3.3 volts. So this is pretty much it about ESP32. It has some GPIO pins where you can see all of these pins here. This is the G4, G0, G2, G1, G18. Well, some of them are analog pins and some of them are only digital pins. Some of them only read and write digital state, for example. Some of them only read and write digital state. For example, if the sensor, if the LED is on, it will write it. If we want our LED on, it will write on the LED pin that it has to be on. So it will put the LED at the state of 1. So on the contrary, if we want our LED to be off, it will write on that LED should be off. So there are only 2 states here, 2 possible outcomes, that either the LED, this pen is providing some of the voltage to the LED, or this pen is at ground zero level of voltage. So there are 2 states on some of the pins, but some of the pins can can read such sensors, which is the analog sensor. This soil moisture sensor outputs an analog signal. So our pen has to be able to read that analog signal to work properly. So this pin G34 is of course the analog pin. So we must have to connect our soil moisture sensor sorry we must have to connect this soil moisture sensor with an analog input. So the ESP32 will read the data, the analog data from that sensor, and display it on our humble OLED display. This is pretty much all of these components. This is DHT22, which is the temperature and humidity sensor, which senses the temperature, of course, and humidity on from its surroundings, and it will write that data on this pin, and we can read that data by this ESP32, and we can display it on this OLED display. And this is the relay. This is the electronic switch for controlling the motor. So these are pretty much all of the necessary components that we'll be using to make our smart IoT based irrigation system, or plant monitoring system, let's say. Let me connect all of these circuit components together. So this is pretty much all of the circuit diagram, how we connect all of the components together, and with ESP32. So let's start with this soil moisture sensor. This is the capacitive soil moisture sensor, by the way, how it senses the relative moisture in the soil. So it uses the capacitive principle. The capacitance between two electrodes changes depending on the moisture content. So whenever the soil moisture around it is high or low, and whatever it is, so the signal will get amplified with this amplifier, and it sends all of this data from that chip to this A pin. This is the analog pin, and that analog pin is in turn connected with this pin. This is the pin number 34, which is the analog pin in the ESP32, and it reads all of the data, whatever this sensor tells to the microcontroller, it will read that data. The moisture content is this or this or this. For example, the moisture content is 20%, 30%, 40%, and depending on the set value of the moisture content, we turn our motor on and off. So this is how it is connected, and these two pins are the power pins for this sensor. The electronics on board on this sensor will need some power to run, so these are two leads, and I am powering those two leads, or this capacitive soil moisture sensor, from this microcontroller, from the ESP32. So this positive pin is connected with here 3.3 volts, and this negative lead is connected in here, which in turn connected with this ground. So the ground means the zero potential, and positive 3.3 or 3 volts is 3 volts, of course. So this is how the capacitive soil moisture sensor is connected with this ESP32. And this is the second sensor. This is the DHT22, which is the temperature and humidity sensor. This also has this data pin and these VCC and ground. VCC means positive lead, and ground means negative lead. So VCC is connected with, let's say here it is. So this is connected with this 3 volt pin, and this is connected with the ground pin of the microcontroller, of course. And I'm powering all of these components, like, you know, the relay, the OLED display, the DHT22, and soil moisture with those same pins, the 3.3 volt and the 3 volt, and I don't know, I'm keep on saying this 3.3, but it is actually 3 volt, and the ground. So all of these sensors are powered on those two leads. So the data pin from this DHT22 is connected with this pin number 25. So this is the digital pin. So the OLED display, OLED has of course these 4 pins, and 2 of them are VDD and ground. Those are 2 power leads for this OLED display, where it gets the power from. And this SCK is the clock pin, and SDA is the data pin. So here it is. The clock pin is connected with, let me confirm from this circuit diagram. The clock pin is, yes, here it is. SCK is connected with D22. So SCK, so yes, it is connected with pin 22. Here it is. So ESP32 is quite large in width, so we have to connect all of these wires beneath that board to get access on those pins. So I've connected these 3 leads, or these 5 leads, for instance, beneath that board. So pin number G22 is connected with the clock pin, and the pump is of course connected like this with the relay. Here I did not connect any of the power external power supply. You know, that's bad. So let's add a power supply. So here is like battery. So search for it. Here is the all of the batteries. So let's say we are using this. Okay, so here it is, and the second end will be connected with, no, well, this end. So this is the proper way to represent how this will work. So we have to include an external battery and use the relay, these two points or these two connections for the relay as off the relay as a switch to control our motor. So this is a proposed circuit diagram, and all of those connections are pretty simple. 4 leads from the OLED display, 3 leads. Of course, all of those components need some external power, so we powered them from this ESP32. To upload a program, we need to connect a USB cable in this port to power this ESP32. Without using this port here, we have to use this pin, the VN pin. The actual ESP32 has this pin, and will power the ESP32. If not connected with any of the PC, we have to use that pin. This is the proposed circuit diagram. I hope you like it. This was the first part in the series of how I built that IoT-based smart agriculture system. I hope you like it, and that's it. First of all, when you start this project, you will have to import, well, the fritzing, the software fritzing do not contain all of these components that we need for our project. So you have to import first. You have to download all of the libraries that we need, like soil moisture sensor. None of the libraries or none of the component present in this software like preloaded. So you have to import all of these components all together by yourself, and here is what you will need to do. So you have to go through this I fast forward that video, and you have to deal with all of this stuff all together by yourself, and eventually you will preload all of those components, and you will be good to go.